Hello, everyone. My name is Rich Ottinger, and I am the Marketing Programs Manager for Park Systems. Normally, I'd be coming to you from the Park Nanoscience Center in Albany, New York, but today we are all at our home offices. Welcome to today's webinar, Recent Innovations in Scanning Tunneling Microscopy and Park SmartScan. Before we begin, let me give you a quick overview of today's session. The presentation will last approximately 35 minutes, after which we will have time for a short Q&A session. Please enter your questions at any time into the questions module of GoToWebinar. If you prefer, at the end of the presentation, you may click the raise your hand button and I will unmute your line so you can ask your question. It is now my pleasure to introduce to you Jiali Zhang, an applications engineer here at Park Systems. Please welcome Jiali.
Thank you for the introduction. Hello, everyone. Good morning, good afternoon, and good evening, depending on where you are. My name is Jiali, and I'm the Technical Services Engineer here at Park Systems. It is my great pleasure to give you the short webinar about Scanning Tunneling Microscopy, or STM, and the recent innovation of Park Systems software, SmartScan. Before we get started, I want to give you a brief introduction about our company, Park Systems. Park Systems is a world-leading manufacturer of atomic force microscopes and emerging nanoscale microscopy systems. We develop solutions for many research and industrial applications, enable advance in science from major universities, national labs, and a wide variety of national companies specialized in diverse fields. Our product line covers just about every usage, with fully manual to fully automatic AFM systems. As you can see here, we have our research product line starting from our XE7 system, which is the most economic choice for research AFM, to our NX high-vac system for vacuum AFM imaging. We also provide you with industrial system from NX HDM to NX 3DM for wafer characterization purposes. In general, our AFM technology offers best accuracy, the highest resolution, and it is the easiest to use on market. If you want to learn more about our company and our products, please visit parksystem.com for more information. So without further ado, let's get started. Here is the brief outline of today's presentation. Basically, the focus of my webinar is to demonstrate the feasibility of STM imaging using Park Systems instruments. After that, I will slightly change the gear and introduce you some of the recent innovation for our data acquisition software, SmartScan, for our users' benefits. So let's first look at the basic principle of STM. STM is one of the application modes for scanning probe microscopy family. It was invented in 1981 by Binninger and Raw at IBM Zurich. 5 years later, they were awarded the Nobel Prize in Physics for its invention. STM is based on the concept of quantum tunneling, with a sharp tip it is conducting, and the tip is brought very near, usually within 10 angstrom to the conductive sample surface to be examined. Bias applied between these two will allow electron to tunnel through the vacuum between them. This resulting tunneling current is a function of tip positioning, applied voltage, and the local density state of the sample. Based on these simplified equations, where you can see that the tunneling current IT is exponentially proportional to the distance between the tip to the sample surface. Usually, with a change of 1 angstrom in distance will cause a change of nearly 1 order of magnitude in current. Thus, this facilitates the high vertical resolution of STM. Here below shows the schematic diagram of STM instruments. Similar to other SPM technology, a feedback loop is employed, which constantly adjusts the Z position of the tip relative to the sample using the Z piezo. The tunneling current can be used as a feedback signal to feed in the computer so that to control the piezo move up and down, thus mapping the sample surface. Usually, this tunneling current have a very small magnitude. Therefore, a current amplifier is needed before it proceeds into an image. Taking advantage of the previous mentioned extreme distance dependence of the tunneling flow between the probe and the sample, that makes it possible for STM to achieve atomic resolution. Therefore, STM is very useful to study surface roughness, defects, and surface reaction in material like catalysts. And STM is also an important tool in research surrounding semiconductors and microelectronics. Despite this super high resolution of STM, there are huge obstacles that prevent the prevalence of STM, such as the cost and complexity of an STM systems. So to overcome these advantages and make STM available for more researchers, Park Systems introduced the STM module, which includes a special designed STM probe hand and an internal no-noise current amplifier. And this STM module is available in all Park Systems research product line, including both NX series or XE series, such as our NX10 systems. As I just mentioned, STM utilizes a sharpened and conducting tip. Unlike conventional AFM, where a silicon or silicon nitride cantilever is used as probe, usually we use a conducting wire. In our case here is a platinum iridium wires. And how do we prepare this wire to make it a probe? We do that using a pulling method. To be specific, this wire was held tight against a plier in one hand and uses a sharp scissor hold 45 degrees on the other hand. By pulling the end of this wire using the scissor while snipping the wire within the plier, a sharp STM tip was created as shown here. Some research labs might utilize chemical etching methods. However, we found out that this non-etching pulling method is very easy and the image quality is good enough for general purpose. Once the tip is prepared, it will be mounted to our special designed STM probe hand. Here you can see the protrusion of the platinum iridium wires. And then we will have a link wire connecting to the STM head extension module, and then through cable to connecting to our internal current amplifier into our NX systems. And this internal current amplifier can have a variable gain from 10 to the 6 to the 10 to the 12 volts per ampere. And our sample chart allows user to apply sample bias with variation from negative 10 to 10 volts. This altogether created the simple STM module assembled into our NX10 systems. To show a static or non-static electromagnetic field of 50 to 60 Hz, you can also assemble the Faraday cage. Once the system was set up, SmartScan software is used to characterize the sample surface. As a proof of concept in this experiment, I used ultra-flat gold surface that was freshly peeled from the mica. And this was done in imaging ambient environment using our NX10 systems. And the tip was previously mentioned platinum iridium wires. And the scanning parameter is showing here. And now let's check out our results. So here shows you our high quality one by one height imagings and acquired by our STM module in NX10 systems. And right side is the 3D views of these height images. You can clearly see the different layers of gold terrace and gold islands. and the roughness is about 3.48 angstroms. And this clearly steps shows you the high resolution of our STM module. So keep zooming the imaging into 500 by 500 nanometer into another area. We can see this 60 degrees angle of gold 111 terrace edge. This is a characteristic of epitaxial gold 111 orientations, which was not usually shown in other AFM systems. The 3D display shown on the right side also shows those terraces were separated by well-defined gold steps. And these gold steps have a roughness about 2.3 angstroms. But keep zoom in this imaging into 200 by 200 image area. The gold step height of this atomic flat gold 111 terrace was quantified into our line profile. And this was done in our data analysis software XCI. And this profile shows you the flat terrace have a single gold monolayer step height about 2 to 2.6 angstroms. This is in well agreement with theoretic value of monolayer gold thin film height. Not only does our STM module enable users to get high quality images showing here using STM tip as a nanometer scale contact, you can also generate scanning tunneling spectroscopy or STS results. As shown here, this STS result provides you a plot of currents as a function of the bias. It can be measured at the selected point after taking the previous STM image, like this mark shown here. And it can be used to study the local electronic state of the sample at designated positions. Since a lot of researcher scientists also wish to use a high resolution of STM to study the chemical and biological reactions, which is usually taking place in liquid environments. Therefore, I want to show you the feasibility of STM imaging in liquid. So I will use the same STM module that's shown before, therefore, and also using the platinum iridium wires. However, the setup has a slightly different. We will have an additional steps. We need to insulate the STM tip with a layer of coating. And in here, I use nail polish paint as a coating material. And to make the coating uniform, you might need coat it for several times and then air dry it for half an hour. And after that, you can eye examine it or examine it in our vision view of our systems on the 10x objectives to see if the coating is uniform, and then assemble into our STM probe hand. And then, since this is a liquid imaging, so we will utilize our liquid cells. For normal researchers, you can use your own liquid cell or use Petri dish. But however, you have to make sure the sample was mounted well. In this case, we use a clip to mount it, and this clip will also insulated with nail polish. And the sample we utilize here is C10 sial coated normal gold, which were created by thermal evaporation. And the liquid I used in this experiment is just DI water. All the other setup is similar. We still need to connect it into our internal current amplifier. And also, we need to utilize the STM probe head. Now let's move out to our results. And of course, this image was still done using our SmartScan software. Here shows you the 2 by 1.4 image area. You can still see this multi-layer gold terrace, and the terrace looks like different from previous sample in air, because this was deposited with thermal evaporation, so different preparation methods. And this line profile still shows you the angstrom height difference between different layers of gold. So in summary, and those above results demonstrate the capability of the Park system AFM in performing STM mode in liquid and in air. And the user-friendly STM module is very easy to set up and is versatile and compatible in all our Park system product lines. Now, on the second part of the webinar, I'm going to introduce you the recent innovation of our data acquisition software, SmartScan. As all our users are very familiar with our SmartScan, it is the operating software for Park Systems AFM, allow new users, especially beginner AFMer, to produce high quality AFM imaging with simple clicks using auto mode. While operating in manual mode, SmartScan provides all the function and tools necessary for experienced users to feel at home. Besides these known features, I want to introduce you the PinPoint nanomechanic mode, which already embed in our SmartScan. This mode allows users to accurately quantify nanomechanical properties such as stiffness, adhesion force, and modulus by collecting force distance curve data in real time. Then I will talk about our new function, SmartLitho, the nanolithography function for enhanced nanomanipulation and nanofabrication. This is a new function that will be released soon in SmartScan in our next update. So first of all, why do we care about PinPoint mode? So conventionally, research rely on one distance curve to acquire mechanical properties by indent a hard cantilever onto the sample surface. It was done one point at a time, and it is pretty local. Therefore, since most of the samples are heterogeneous, to get a full picture of the mechanical property of the sample, it is necessary to get both a distribution image and a quantitative data simultaneously. Now the question is, how do we do that? So in making the practice possible, Park system PinPoint modes provide the most effective method to acquire nanomechanical mapping with high speed and accuracy. So how do we do that? Is that during operation, while measuring sample topography, the XY scanner stops at each acquisition, and during this pose, the Z scanner takes a rapid force distance curve with fine controlled force, distance, and contact time between the tip and the sample surface. And we do this approach retract reactions at each pixels. So for say we have 256 by 256 pixels, then in total, we will have 65,000 force distance curve generated. And once the cantilever diffraction reached to our designed force threshold, the Z scanner height recorded and then help us to get the topographic information. And then after collecting all the force and different distance curve at each pixels, how do we get all the stiffness, adhesion force, and modulus? It's based on calculating, analyzing the force distance curve at each pixels. For example, the stiffness was the slope of the force distance curve, and the y-axis of this is the adhesion force, and the modulus was calculated by the 2 points selected by the user using Hertzing models. And finally, and in PinPoint mode, all this force distance curve were calculated and generated and plot into the distribution and output as image showing here. And this is polystyrene low density polyethylene samples, and with topography, adhesion force, modulus, and stiffness. And here you can clearly see how our software output live force stiffness curve at each pixel and quickly result in the mechanical property mappings and within just 20 minutes. So another recent innovation in our SmartScan is the SmartLitho, which is a nanolithography using SmartScan. And it is a controlled nanomanipulation via Park Systems nanolithography mode, allows you to manipulate or create patterns through a controlled applied force or voltage, such as bias mode or Z-scanner mode or set point mode. And this is a screenshot of our nanolithography panels in SmartScan. As you can see, this is still under development, and we will release the software upgrades soon in the summer. So if you want to know more about the SmartLitho, you can contact our technical support teams. And on the left side, you can see you can clearly choose different control modes from Z-scanner mode to bias mode, and also set up different control parameters. In the middle, you can design your lithography features and using previous scanned AFM image as imaging cameras. And right side is for each features, you can precisely control whether the length and the scanning parameters and also the set point or applied bias. And as a proof of concept, I will just introduce you the result of bias mode. So bias mode is the basic principle of bias mode is that it utilizes voltage poles applied between the tip and the sample surface to generate an electric field, and which allows local oxidation to be used to form the oxide feature on the sample surface. Usually we use silicon as substrate and thus generate silicon oxide. The water thin film formed on the surface is important as it plays important role to forming the oxide. The amount of water molecules and the voltage applied will determine the amount of ions and available for oxidation reactions. The negative charge ions will flow away from the bias tip and react with the silicon molecules and that form silicon oxide on the surface. So now let's move to our results. And this result was generated by the bias molding using our recent SmartLitho software. And then this feature showing here is topographic imaging and lateral images, and the corresponding line profile cursors. The feature is concentric circles with an average height about 2.5 nanometers and width about 150 to 200 nanometers. And to summarize, in this webinar, I have showed you the ability of Park's NX series AFM in performing STM in liquid and in air, as well as our recent innovations in SmartScan software, such as PinPoint mode and or SmartLitho mode, which allows you to get the simple modules or manipulate the pattern on the sample surface through applied force or voltage. In conclusion, our Park NX series AFM offers the most versatile AFM STM system for diverse applications, and that's pretty much it. And thank you very much for your time and listening. And for more information, please visit our website or contact our sales for inquiries. Or for current users, you can contact our tech support team for application or technical questions. And with that, I'm happy to take your questions.
All right, thank you very much for the presentation. We do have 2 questions so far that I will ask, and if anybody else comes up with a question, please use the raise your hand feature or type it into the questions module. First question is, how do you quantify tip radius?
Okay, so in general, the tip radius can be quantified with SEM, but in our systems, you can get all the radius and specifications in SmartScan software, and also we have all the specifications when in the spec sheets when you purchase our tip from our companies.
All right, and the next question was, what is the latest SmartScan software that is available?
The latest software is RTM12D. And if you are using the previous versions, you can email techsupport@parksystem.com, and we will provide the most updated SmartScan software.
All right, and it looks like we have 1 hand raised, so I will try to unmute the line for you, Riza. Can you ask your question?
Hi, can you hear me?
Yes, we can.
Yeah.
Awesome, thank you so much. So I already typed my question, but I can actually ask you right now. So I wonder if it's possible to mount the self-fabricated cantilevers, because in our research group we are fabricating special type of AFM cantilevers. So I'm interested to see if it's possible to mount our cantilevers into your NX10 AFM tools, or we should buy a specific mounting mechanism, or we have to design it. How have you been in any situation that you need to mount any like a non-standard AFM cantilevers on your systems?
So I'm still assuming that your cantilever is rectangular cantilever beams. And for that kind of cantilever, yes, we can provide you a mounting ways. There are 2 ways. First, you can use our provided clip type chip carriers that should come with our NX10 systems when you purchase our systems. For that, it's use pressure to mount your cantilever, your own unmounted cantilevers, and therefore you can assemble it to our a probe hand, or you can use a super glue to mount it to our chip carriers as well.
Okay, and is there any specific information on the website that I can take a look at them?
Yeah, we do have. You can visit our website, check for probe hand or mounting unmounted probe, and or you can just email the customer support. I will provide you with more information.
Okay, thank you so much.
Thanks for the question. We did a couple more that came in, so I will ask those. Can one do conductive AFM with PinPoint, but with IV curves from every point?
Yes, that is possible. And we do have a webinar, I remember, in YouTube channels that it's conductive PinPoint AFM. You can look more into that or go to our website. And also, you can do just IV curve using spectroscopy mode in our SmartScan software. There is a function called gradients that allow you to do 32 by 32 or 64 by 64 grids instead to do the IV curve at each pixels.
All right, next question is, sorry, it just moved on my screen. What is the difference between the images obtained in regular imaging mode and PinPoint mode, resolution and speed? Thank you.
Okay, so regular FM mode just allows you to get topography image, and which is a key component for all AFM mode. But PinPoint mode also allows you to get additional modulus, adhesion force, stiffness, and adhesion energies in images at the same times. And also it is a quantitative information, so you can get the numbers out of the images from our PinPoint mode. And for the speed, it all depends on how many pixels you choose. In this case, with 256 by 256 pixels, it takes about 20 minutes. And also, it also depends on how fast you move the probe from one position to the other positions.
All right. Next question. How do you get high resolution scans of insulating oxide surfaces?
For insulated oxide surface, and are you just if you are just talking about topography image, and I don't think there's any difficulty in acquiring those using our non-contact mode.
Okay. Can STM be used to study the surface of non-conducting organic molecules self-assembled on a metallic surface and get to know the alignment of molecules?
I would say the answer is yes. As long as you deposit the molecules into a metallic surface such as gold or HOPG, you were able to see the self-assembled monolayer on surface. So a lot of researchers that do a simple STM experiments using SIO and deposit it into gold to see the SIO self-assembled monolayer of SIO on surface.
Okay. Next one. Could you suggest some ideas for cell imaging in liquid when the adhesion is too high? I cannot get a flat baseline for the maximum setting possible.
Okay, so usually in liquid, it will reduce the adhesion force. But if you think that adhesion is too high, you can also use our PinPoint mode to acquire liquid imaging because it's doing approach and retract at each pixel. That should reduce your adhesion force. And also you can kind of coating your tip with some chemical molecules that reduce, such as non-adhesive molecules to reduce the adhesion force. I will usually use some silane coating to the tips before doing the image. And this is a very acceptable coating methods for AFM probes. You can just log website and Google silane coating for probes, and then you will get the protocols.
All right, here's another one. With regard to the question of quantifying the radius of the tip, I understand that at the beginning I can get it from the information provided by the software or the information from the tip that I buy. But if it wears out in the process, how can I quantify it?
Usually, if you imagine, you can see it from the images you have taken. And when you talk it from the beginning and in the end, when you see some of the artifacts that such as the granule domains become bigger, or you see some of the triangle features, and that means the radius of the tip is getting bigger and the tip is getting down. And that is how I quantify. I use AFM imaging as a way to see whether my tip is good or not. And also another way to prevent tip from doubting is that you can use non-contact mode instead of using contact mode or tapping mode, because non-contact mode prevents your tip from touching the surface and while maintaining the high resolution images.
All right. Why is it possible to image varying topography of cells in liquid mode using PinPoint but not tapping?
For PinPoint mode, it's completely different from tapping. Because I think you think PinPoint is similar as non-contact, but it's different. For PinPoint, it's taking force distance curve at each pixel. Therefore, at each pixel, they will lift up and move to the next position. And the lift height will be several hundred nanometer or 1 micron depends on how you define it. And since the lift height is so tall, therefore it will definitely pull your away from the adhesion force regions, which is within 1 nanometer or 5 nanometer regions.
All right, here's another question for you. How do you calibrate your scan piezo? By taking Hop-G atomic images? If that's true, won't the calibration change with the change in tip length?
We do have a calibration sample, but it's not what you stated. This calibration sample is usually what we call 100 mg. It's a predominated height calibration standard with a height about 100 nanometer, and it's consists of silicon oxide structure on silicon chip. And the silicon oxide structure usually have 10 micron or 5 micron pitches that's used to use for XY axis calibration. And the XY and the calibration will conducted periodically to ensure the AFM scanner work with high precision and high accuracy. And I don't see why the tip radius will affect the calibration.
All right, thank you very much, Jia Li. I think that we're going to wrap it up there for today. If I didn't get to your question, I will go through everything that's been entered and make sure that we reach out to you with an answer for your question in a follow-up email. Keep a lookout for more upcoming webinar announcements over the next few weeks as we try to increase our online activities. The next one scheduled is on Friday, April 17th, once again at noon Eastern Daylight Time, and features Dr. Rigoberto Advincula of Case Western Reserve University. You can register for that at parksystems.com/webinar2020. Thank you all for joining us for this session. You can find more information about Park Systems AFM at parksystems.com. And please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions about this webinar, feel free to reach out to me directly, and my email address is richard@parksystems.com. Thank you all very much, and we hope to see you at another session soon.
Thank you.